So today we will be focusing our attention on this section 1.7, which is about whether the given vectors are linearly dependent or independent. Okay, so one of the most important concepts that we'll be talking about today's class in this section is whether the given vectors are linearly dependent or independent. Now, what is so what is the definition of linearly dependence relation or linearly independent relations? So what it means is, okay, let us read this definition together, okay? An index set of vectors, b sub 1, b sub 2, all the way up to b sub p in Rn is said to be linearly independent if the vector equation, okay, this is a vector equation, x sub 1, b sub 1 plus x sub 2, b sub 2 plus all the way up to x sub p, b sub p equal to 0 has only the trivial solution. Okay, so that means, what it means is, trivial solution, you know that. The solution is all zeros, okay? So let me, here I have written x1, b1, x2, b2, and here c1, b1, it's the same thing, okay? x1 and c1 are the same thing. Let me just write down this, change it into x1, x2, all the way xp. So linearly independent means x1 equals 0, equals x2, equals x3, all of them are 0, okay? It has only the trivial solution. And the set of vectors are said to be linearly dependent if this vector equation, in this case, some x1, x2 or xp, some of them are not 0, okay? At least one of them, one or more of these weights, one or more of the scalars are not 0. Then we call it linearly dependent, okay? So if you want to write this in matrix form, okay? So in matrix form, what we can write is this. Remember, so linearly independent. So from now onwards, I simply write Li, okay? Linearly independent means x1 v1 plus x2 v2 all the way up to xp vp equal to 0, then it has only the trivial solution. That means then x1 equals to x2 all the way up to xp, all are 0. And if you want to write this in matrix notation, what we can write is matrix equation form. We can write this as, remember this one, v1, matrix equation means ax equals 0. So we are talking about homogeneous equation here. So matrix A means it, the vectors are the column of the matrix. So b1, b2, all the way up to bp. So this is our matrix A. And x means x1, x2, all the way up to xp equal to 0. And this system has, x1, x2, all the way up to xp equal to 0, okay, in matrix notation. So this is how we define the linearly independent vectors. If some of the weights, some of the scalars are not 0, then we call it linearly dependent. In another word, if the vectors are not linearly independent, then they are linearly dependent. All right. Now the question is, Okay, let's look at a simple example here. So we are given 3 vectors and we want to check whether the set of vectors is linearly independent. So it means what we are supposed to do is, let us consider the vector equation. Okay, so consider vector equation x1 v1 plus x2 v2 plus x3 v3 equals 0. All right, so that means, or if you want to write this in a matrix form, you can write this as ax plus b form, or in matrix form you can write v1 v2 v3 and x1 x2 x3 equals 0. All right, so you can write this way. Now the question is, if all x1 x2 x3 all of them are 0, then we call the vectors are linearly independent. So that means we need to figure out the value of x1 x2 x3. In another word, we need to solve this equation. All right, we need to solve this system of equation. Now how do we solve the system of equation? Let me just write down this way. X1, or maybe you can write this, what is x1 x2 x3? I have not defined it. Let me define that, where x1 x2 and x3 are scalars, or you can say weights. Okay, so you can also write, or you can write x1 v1 means simply 1 2 3. Let me write this way. Now we need to solve this system. Okay, so now we need to solve the system. So in order to solve the system, you can consider the augmented matrix. So the augmented matrix will be, for this, let us consider augmented matrix. So augmented matrix will be v1, v2, v3, and 0, right? So that will be your augmented matrix. So what it means is v1 is, we already know v1 is 1 2 3, v2 is 4 5 6 2 1 0, and then 0 means 0 0 0. So the 0 vector is 0 0 0. Now please change it into echelon form. Change to echelon form. Okay guys, take a few minutes and try to change it into echelon form, and I'll wait for you. So changing the given augmented matrix into echelon form, this is what we got. So the first row is 1 4 2 0, and the second row is 0 1 1 0 and 0 0 0 0. Now in this case, you notice that the basic variables are x1 and x2, and free variables is x3. Recall from the previous lesson, we have discussed already that if the system has free variable, that means it will have non-trivial solution also, right? In order for the system to have trivial solution, there should be no free variable. So free variable means there exists non-trivial solution. So free variable means there exists non-trivial solution. Okay, in another word, in order for this system to be this system, let's say this is equation 1, in order to satisfy this system, it is not necessary that x1, x2, x3 all are 0. There may be a possibility that, you know, some of them, x1, x2, x3 are not 0, and still this equation will be satisfied. So just keep this in mind. When there is a free variable, it means there exists a non-trivial solution. That's what we discussed in our last class. So if there is non-trivial solution, then the vectors are linearly dependent by definition. So we have just discussed the definition. So the set of vectors is linearly dependent. Okay, from now onwards, I simply write LD for linearly dependent vectors. That's it. Right? To check whether the given vectors are linearly dependent or independent, what you need to do is, all you need to do is change it into echelon form. Okay, consider the augmented matrix, change it into echelon form, and see whether there is any free variable or not. If there is a free variable, then the vectors are linearly dependent. No free variable means independent. Okay, so let's look at, let me write this. This is very important. Please remember, free variable means this represent linearly dependent. No free variable, that means only the trivial solution, which means linearly independent. Just please remember this. Very important idea. Now let's look at another example, and you may want to try this on your own. Okay, so example 2, determine if the column of the matrix are linearly independent. So the column of the matrix, that means this matrix has 3 vectors. So let's say this is V1, this is V2, and this is V3. Now, basically what you do is consider the matrix equation or vector equation, doesn't matter. I think since we are given the matrix, it will be easy for us to consider matrix equation. Okay, matrix equation AX equals 0. Notice that all the time I'm considering the 0 on the right hand side, and that's what you need to do by definition. Consider the homogeneous system of equation. So that means A is already given, where A is 0, 1, 4, 1, 2, negative 1, and 5, 8, 0. X means x1, x2, x3 equals 0 means 0, 0, 0. Okay, this is the matrix equation. You can consider vector equation also if you like. So you can write this as x1 v1 plus x2 v2 plus x3 v3 equal to 0, and then consider the augmented matrix, which is b1, b2, b3, and 0. You can consider that way. Or from here, augmented matrix will be augmented matrix is 0, 1, 4, 1, 2, negative 1, 5, 8, 0, and then 0, 0, 0. So this is your augmented matrix. Please change it into echelon form. And then try to figure out whether there is any free variable or not. Okay, take a few minutes and let me know what you get. Okay, interchanging R1 and R2, that's what I got. One, and then you do yourself whatever is required. And so your final echelon form will be so we got, the echelon form as this here, right here. And now the question is there any free variable? If there is any free variable, that means the system is linearly dependent, and no free variable means linearly independent. And clearly you can see that there is no free variable. Okay, so since the system has no free variable, the set of vectors, I mean the vectors, I mean the column of the matrix, the vectors which are the column of the matrix, the vectors which are the column of A are linearly independent. Considering the matrix, I mean, considering the system of equations, and then considering the augmented matrix changing into echelon form, and figuring out whether the system has any free variable or not, that is the general method in order to check whether the vectors are linearly dependent or independent. But there are some situations where you can just tell just by looking at the vectors. You don't have to do all of these process. Okay, and you can make your life so easy. Just just by looking at the vectors, you can tell whether the vectors are linearly dependent or independent. That's what we're going to learn now. Okay, so let us see. Set of one or two vectors. If we are given one vector, only one vector, for example, if we are given, let's say 1, 2, 3, for example, then this one is always linearly independent. Okay, one vector is independent. There is no other vector that depends on that. Okay, just linearly independent if there is one vector. If there are two vectors, then if they are multiple of each other, then they are linearly dependent. No multiple of each other, linearly independent. Okay, let me show you one example. Suppose V1 is 1, 2, and V2 is 2 and 4. And let's say V3 is 1 and 5. Now, V1 and V2 are linearly dependent because they are multiple of each other. Okay, because V1 and V2 are multiple of each other. Multiple of each other. V1 and V3 are linearly independent. Okay, I'll write Li, linearly independent, because they are not multiple of each other. They are not. Remember, they are not multiple of each other. It's that simple. Now, let me ask you one question. V2 and V3, are they linearly dependent or independent? Clearly, V2 and V3 are not multiple of each other, so they are linearly independent as well. Okay, So just keep that in mind. So you don't have to do all that process. Now, what it means is, suppose, let's say my V1 is 3 and 1. And if I draw the vector, this is 3 and 1. And let's say my vector V2 is 6 and 2. Then this is my vector. So these V1 and V2 are actually multiple of each other. So if you draw the graph, then they lie on the same line. And in that case, we call them linearly dependent. So sometimes if I give you a vectors in geometrical form like this, and if you notice that the vectors lie on the same line, that means they are clearly multiple of each other. So they are linearly dependent, okay? Linearly dependent. Now let's look at this example. Let's say this is U1, which is 3 and 2, and U2, which is 6 and 2. Now, these are not multiple of each other. So if you draw the graph, you notice that they do not lie on the same line. So they are linearly independent. Okay? So let me ask you one thing. If I have a line here, let's say this is one vector, this is another vector, this is another vector, this is V1, V2, V3. So they all lie on the same line, therefore they are linearly dependent. And if they do not lie on the same line, that means they are linearly independent. Just keep that in mind. Now, okay, so example 3, we have just seen it here already. So this one is 3, 1, and 6, 2. Linear, they are multiple of each other, which means linearly independent, dependent. And 3, 2, and 6, 2, they are not multiple of each other, so linearly independent. All right. Now, here is one theorem. Characterization of linearly dependent set. Okay, an index set S, which includes the vectors V1, V2, all the way up to BP of 2 or more vectors, is linearly dependent. Let me repeat that. Linearly dependent, LD, if and only if at least one of the vectors in S is a linear combination of the other. So what it means is, this is the same vectors that we work in example 1. And we have already proved in example 1 that they are linearly dependent. Okay? And if you don't want to use that method, and if you just want to use your common sense, even though common sense sometimes is difficult, okay, if you're very sure using the common sense, go for it. It saves a lot of time. Otherwise, you can follow the method that we learn in example 1. So when I look at this, after lots of practice, you can tell right away what is the relationship between these vectors. Okay, you can just tell just by looking at this. So for example, in this case, what I can see here is that one of the relation between the vectors is, if I multiply this V1 by, let's say, 10 V1 minus 5 V2 plus 5 V2 equals 0. Can you check whether did I write the correct relationship between V1, V2, V3? Or you can write simply, you can write 2 V1 minus V3.
It should be V3 on the last one, right?
V3.
Yeah, V3. Let me just write this way. I think that will be easier. So let me write 2 V1 minus V2 plus V3 equals 0. Is that relationship is true? What I what I saw here is that, you know, there is 2, there is 1. So if I multiply that by 2, then if I subtract this V2, then 2 plus 2 is 4 and minus 4 is 0. In the same way, I just think in my mind, you know, using common sense, and I notice that this is the relationship which actually satisfy for all of these other entries as well. Okay, so that means what I can write is, if I solve it a little bit, I can write V1 equals half V2 minus half V3. Okay, I can write this way too. So now going back to the theorem, it says that if you can express one vector in terms of the other vectors, then the set are linearly dependent. In another word, V1 depends on V2 and V3. Okay, so remember, V1 is actually expressed in terms of V2 and V3. That means V1 depends on V2 and V3. Remember, in high school, we have seen that x equals, let's say, you know, 2x plus 3. Then what we say is that y depends on x. So x is independent variable and y is dependent variable, right? So in the same manner, so here V1 depends on V2 and V2. So we can say that V1, V2, V3 are linearly. So the set, so V1, V2, V3 linearly dependent. That's one way of looking at it. Okay, this is sometimes easy. And if you find this difficult to use the common sense, then you already have the method that we learned in example 1. No issue there. So whatever, you know, you find easy, go for it. Okay, now another method is this. Here is a theorem. If a set contains more vectors than there are entries in each vector, then the set is linearly dependent. Remember, more vectors than the entries. Now let us look at this example 6. How many vectors are there? 4, right? There are 4 vectors, v1, v2, v3, v4. Now, how many entries in each of the vector? 3 entries. So here, 4 vectors, and each vector has 3 entries. Then by theorem 8, they are linearly dependent. Okay, I call this, you know, I call this short fat matrix. You see, short, it's short, but it's fat matrix is dependent. Because you see, there are 4 of them, but the height is only 3 feet, but you know, the width is 4 feet. So it's a short but fat matrix. And even short and fat people, they depend on other people, right? So I'm just kidding. Anyway, so this is one way to memorize. You know, when I was a student, I memorized this theorem this way. Short fat matrix is always linearly dependent. Another theorem, theorem 9. If a set S equals B1, V2 all the way up to BP in Rn contains a 0 vector, then the set is linearly dependent. So if the set contains 0 vector, linearly dependent. For example, in part B, this vector contains 0. So this is linearly dependent. You don't have to do. If you want, you can still apply the method that you learn in example 1. Even for this part A, part B, you can apply that method. And notice that, you know, when we apply that method, it took a lot of time, right? But if you know that it is a short fat matrix, you don't have to do this. According to this theorem, we can say that it is linearly dependent. If you see all 0 vectors, you know, at least 1 0 vectors, then you can simply say that it is linearly dependent. You don't have to, you know, use the method that we learned earlier. Now, part C. What do you think? Is it linearly dependent or independent? Okay, so part C, as we have seen, they are not multiple of each other, but it's a little tricky. You see the first one and second one, if you look at the relation, then it works like V2 equals negative 3 over 2 V1. And it works for the second entries in both third entries, but when we look at the fourth entries, then it doesn't work. So therefore, they are not multiple of each other. So they are linearly independent. Okay, no multiple of each other, linearly independent. So we are almost done with this section. And here is one practice problem. And I would like you to look at this and think about what are the possible answers for all of these, 1, 2, 3, 4 yourself. And if you need any help, then we'll discuss that later. Yeah. So try this on your own, okay?